Hello, so today I have the pleasure to present Professor Zakarya. He is a professor at the Utah University in Jordan. The title of this presentation is Cell Detection in Biomedical Immunohistochemical Images. This talk will be about the accurate computer-aided cell detection in immunohistochemistry images of different tissues. And this is something which is essential for advancing digital pathology and enabling large-scale quantitative analysis. From the image analysis point of view, we are facing a new image segmentation and target detection problem. And Professor Tawaneh, he will present different unsupervised segmentation and deep learning techniques to address this problem. So thank you very much.
Thank you very much. Okay. Thank you for everybody here. Thank you for being here. Today, I will present. Okay, I have some problem here. Okay. I think without the clicker it's better. Yeah. Quantitative analysis is real in terms. Sometimes real in terms like high stain, low stain, without a stain, which prove insufficient precise of diagnosis of cells. So we need to move to a quantitative analysis to count or to accurate count and classify cells of mouth tissue of for cancer of leukoplakia with various of dysplasia, especially for biomedical like K67. Already, the immunohistochemical image contain a critical tissue behavior, so the solution for our problem is to move from the qualitative analysis to quantitative analysis to make the decision. It's more easy for the decision maker while they treat or diagnosis and check the prognosis of the types of cancers. Already we deal with K67, which is approved vibrations for or a protein. This protein used to for the clinical site to detect the type of cancers and detects the how much it's progressive in the field. Our research question: which approach, unsupervised segmentation method or supervised deep learning methods or models? We already use UNIT and YOLO, achieve more accurate and reposit cell detection in immunohistochemical image. This is the core of our research. We aim to, in this research, to develop an automated high accurate method for qualifications, the cell detection in K67 in immunohistochemical image of oral cancer tissue, thereby enhancing diagnosis precision and treatment planning by effectively distinguish between high stain, low stain, without stain for a nuclear cell, and develop the computer vision based method to automatically detect and classify stain cell in immunohistochemical image. And we will try to bridge the gap between the qualitative observation and quantitative analysis for improve the diagnostic accuracy. To achieve these objectives, we utilized a data set of oral immunoanalyzer database data set, which is already available in this link. Already we have 40 high resolution image. Each image contains from 343 to 2,000 and more cells, with the average bare cells, okay, for all of 40 image, exceed 1,000 cells. Each of we show here the diagram that show the variety of the level of staining for all, or for average of all of image, and each image have its variety. Now we will present some of these image of immunohistochemical image to involve you what is the problem and how can we detect. This is one of these image. For example, here there is nothing determined except this circle to show you some. There's many cells. No one can detect the cells except the expert. So, and there's a variant between the expert of detection. So here we see some high stain and low stain and without stain level of cells, but where is the region interested area. Now we show you this is only between the red lines. This is the region interested area for the expert. The outside, it's not cells, it's just a protein. Okay, here we show you some variety and diversity of the staining level. We see here the high stain level and low staining level, and this is the low staining level, the red, the green one, and the high, and the blue one, it's without staining. Another problems we can show it from this image. Okay, again, you can use the table to follow up the staining level. Another thing is we can see the overlap between cells and difference intensity between the image. Many problems we can deal with that image of immunohistochemical image. We have a problem of image segmentation and object detection, but we can address this problem from two perspectives: unsupervised methods, segmentation, and supervised segmentation method. But in this presentation, I will concentrate on the supervised segmentation method, because already we published a paper in 2024 using the unsupervised method, which is already have 6 algorithms. We count and classify and at the end evaluate number of cells and counting that cells. In this presentation, I will show again, but in using a new perspective, which is supervised learning. Okay? All of these techniques already validated method against the pathology annotated data set. Our data set before, we're showing here, all of these cells annotated by experts. Okay, but we will fastly move to unsupervised quickly. This is the paper already published. Okay, we have a link, and this is the software related to the same paper software. And now we come back to the supervised. In supervised, we have two art of state methods, YOLO and UNet. Okay, we use YOLO to detect or allocate cells using the heat map, which is the way that we use YOLO on it, and UNet. And YOLO, we can detect the object, okay, using the bounded box on the trained patches, which is one of our methods we follow in this paper. Training by our patches, which is already extracted from our data set, and feeding to the model. We use, to evaluate that, we use a leave one out image, and using the precision for more evaluation to ensure the fair between the two methods that we used. Okay, but before we starting talking about the methods and the procedure that we follow in these methods, we have a little challenge, okay? And we will show you how we deal with that challenge. The first challenge, data scarcity, because we only have 40 image, but it's high resolution image, okay? And we show you how we deal with that. And the overfitting, because this is the common problem for the deep learnings. If these two problems found in any models, that makes the models very poor, so we solve that problem. We solve the data scarcity, okay, by identify the image, then divided it into non-overlap patches with a limited size as in for the determined for input for the unit, and we ensure that in each patch there's at least one cell. From this solution, we increase the number of image, enrich our image into 2,200 patches. Okay. The second problem, which is the overfittings, to enrich our dataset and to reduce overfittings, we produce image augmentations methods or apply image augmentation methods. We're using rotation, translation, flip, rotations, brightness, zoom, scaling, noise, many techniques, okay, to slightly a variation of the input image to make it different from the input. Then we feed it to the models. Why we do that? Because we want to prevent the model from knowing the same image in the second batch, to prevent this model from this action. So we solve this problem in using this type. After that, now we come back to the models and return to our supervised model. The first model, unit, we already making a batches process and divided the image into batches. Then we using the heat map to generate a probability map, okay, using a spatial location to select the peak of each centroid cell, okay, to detect, to make the detection is more easy using, we'll see there's a threshold, there's a diameter determined by experiment to detect the best cells, and we get a good result with using that, okay? And then we making augmentation for the data and feeding that model with data, and we have a good result in that. Now I will show, this is the batches, okay, which is part of image, okay. This is the ground truth which is already annotated by expert, and this is the heated map. We train the unit using it. You can see, you can check every cell already detected by heated map, okay, and showing heated map, which is the way that we train our unit model. Okay, another example, okay. The second art state, YOLO, which is a common supervised learning model used to object detections, suitable for medical application. Okay, we use the same steps and put the model in the same steps after we divide the batches. We split it images into batches. We feed the batches into YOLO. Then we apply the transform learnings. We already here using a pre-trained model, because in the unit we start from the scratch. Here, starting from using pre-trained models and then trained the same model on our data set. Okay, we use COCO pre-trained, which is, I think it's a famous data set of computer vision, contain many category of image and contain more than 200,000 of image of people, of cars, and etc. Okay, the YOLO already predict the small bounded box around the centroid. Then the output we have the centroid cell. Okay, we determine the size of box 11 by 11 because we focus only on the centroid of the cells, not the all area of the cells. And this is the confidence. Okay, and we use the loss functions. Loss functions, we combine two loss functions for unit. We're using the binary cross entropy and weighted mean square. We're using the binary cross entropy to separate the background from the cells. Okay, and we use the weighted mean to empower the cells itself, the centroid of cells, and giving that functions the highest value to detect. Okay, about YOLO, we already use the default loss function. Okay, which is already an arithmetic library in Python with its components. This is the sample for deep learning models and the results when we apply both of method, unit and YOLO. We can see here the detections, the blue one for the ground truth and the red one for the cells already detected by the system. We can see here, it doesn't matter if the cells, if the ground truth is detected or annotated by the expert in the centroid or not, because we focus in our methods to select the centroids, and we have a diameters to check any point around this value and make it as a point, and to avoid the overlapping between the cells. We can see here the difference between the YOLO and unit. We see YOLO is the best of the selections and finding the more than truth cells of YOLO. Okay, now we show our results. We're starting with the heat map. Before explaining the heat map, I want to show you for you there's a threshold between 0.1 to 0.9, which is represent the value. Any cell exceed this value, or any value exceed this threshold, it's mean a predicted cell or a good cell. We can use it. And this is the diameter to check the distance between the centroid of the cell and the as a radius for the cells. Okay, and each value here, you can see here, means that it is the average of all image of all patches applied depending on this is threshold and this is diameter. So we have a large computation here. It exceeds 500 of files for each one of system, and we took the diameter starting from 10 to 30. We try to check exceed 30, but we cannot. In that case, we do not find any valuable value in that case. We can see here in green, okay, it's the best. This is the scale from 0 to 100. The red is the worst value. The green is the best. Okay, we can see here the balance already in the when we're using a unit model, but we can see again a little bit difference with YOLO. Already, this is the precision for YOLO, and for unit. This is the recall, it's evaluation for unit, and this is for YOLO, and this is the F score, which give us the why we prefer unit model, because there's a balance between the recall and accuracy and precision. Okay, this is the performance of matrix for supervised and unsupervised performance. We see here the dominate of supervised learning on unsupervised. Unsupervised already I explained. We have 6 methods. Here we took only the best 2 methods of them to comparing them with the supervised learning. Okay, so the best here the average, and this is the standard deviations. Okay, for the precision, this is for the recall, and this is for the F score for unit and YOLO and unsupervised, which is already combined between the best 2 algorithms, region detection area and edge detection area. And this is another sample showing by drawing by lines the dominate of supervised on unsupervised. And we see YOLO here, and unit here and here. Okay, this is the deep learning model. After applying that deep learning on the whole image, we get this result for unit, which is already provided by detect the cells, and this is the result for YOLO. Okay, there's a little bit difference between them, but we can, as we can see here, while deep learnings are supervised, super accuracy for clinical application, unit best of overall performance. Pardon. Okay. Okay. We see unit the best overall performance with F score 75.3, and YOLO the faster but slightly lower accuracy. It's okay. Okay. In traditional methods, without any clicker, we remove every 3 clickers, but it's okay. Anyway, try to finish. Okay, the method using already in classical method, we use already region detections and edge detections. This traditional method, still we need it in laboratory because it is very fast. It's not need labeling, okay, but unfortunately it's low accurate. Okay, so but we find the region detections, okay, get the high precision. Okay, high precision but low recall, and edge detections balance precision without any. It's just. Okay. We move to our future work. Our future work, expanding deep learning, and included the deep learning in our software, or the analyzer software, and we will try to expand the data set and applying it into another types of cancer, and to increase the variety of that, and applying these methods in another types of cancer. Okay, thank you very much. Any question?
Thank you. So thank you very much for the presentation. We have some time for questions. So I want to remember that this is part of the doctoral meeting. So what we are presenting here are work in progress, which is it's being developed towards the obtaining a PhD. So the work is still, as he explained, it's still going on. So, well, I have just one comment. The presentation, personally, I liked it. I think it was very focused on the important aspects of the research topic, which I think is good. Only maybe the duration was a little bit longer than it was scheduled, and normally for this we try to focus on short presentations of maximum 20 minutes. But yeah, I think you really covered the important aspects. So are there any questions from the people here? Yeah,
I have a question about the robustness of your approach. How does your model take into account particles with complicated aspect ratios? For example, I see that here all your cross sections are circles, but what if you have an ellipse? Would it consider to be 2 particles or a single particle? Does it introduce error in the model?
Mm-hmm. Can you repeat your questions, but focus on the main idea, because I cannot get it as well to answer you.
Yes, my question is,
robustness, what you need of...
or cells would not be circles, but they would be ellipses. Would that be a problem?
Yeah, about cells.
Yes.
Cells not detected? You ask for the cells not detected, or the cells overlapping between cells?
No, I think it's more about the shape, because we were assuming a circular shape.
Yeah.
And his question is about what happens if it's a different shape. For example, an
Okay.
ellipsoid.
Okay. Thank you. It's a good question, Daniel. Thank you. Our models have a 2 perspective. For example, we use in UNIT, we focus on the peak of the centroid cells. We do not. It's not our potential to detect the shape itself. We're using the Gaussian, okay, to empower the values depending on our thresholds. We use a threshold, and to pick up that values, okay, in unit. So we created the heat map to do that and to select that values. In another model, YOLO, we use the bounded box, which is only 11 by 11. For example, the original diameter is 20 over 20 for the cells, but we have 11 over 11 because we concern of the centroid of the cells. We depend on the centroid of the cells of both of techniques to select them. So there's a confidence that's proved, for example, in YOLO, if there's a cell or not. We don't care about writing or to draw the circle and find the shape of the circle because there's overlap sometimes because the shapes of cells is too different. This methods already we process and find the solution in the classical method in the first paper, not in this paper, because in this paper only we focus on the centroid of the cells for with two different supervised methods. I don't know if I answer you. Okay, don't hesitate to ask.
Second question. So, if I understood correctly, you are just counting cells. You are not measuring their size, right?
Yeah. Yes. In this paper, we concern of counting. Counting, because we need to move from comparing between the method to count and detect the cell itself. Okay, we need to move to quantifications in this and comparing the quantifications using many algorithms, supervised and unsupervised techniques.
With any other question? No? Just one question. With respect to the unsupervised techniques, which were much worse, you show a comparison in which I think the YOLO and UNED were about almost 80%, 77%
yes.
in performance, whereas the unsupervised methods were below 50%.
Yes.
However, I think, well, then the slides were moving, but at the end you show one in which you said with the unsupervised method it was 70%. So I'm confused about the percentage of accuracy for the unsupervised methods. And also my question is, how did you choose which unsupervised method to use and whether it could be a different if you use some other unsupervised method?
Unsupervised. Okay. I mentioned before, unsupervised already we covered in the previous paper. But we select 6 algorithms. For example, we using region detections and edge detections, graph cuts, Chamvays, many of algorithms. For example, we use OTSO methods to determine the optimal threshold to using while we're using canny filters to detect the cells and etc. The traditional method or classical method already damaged when we face some noise. It's difference depending on the clear of the image, etc. and need more and more pre-processing methods. And it's depend only on the similarity of the betweens and the neighborhoods and the discontinuity of some features. But we moved to supervised techniques because it's care of the centroid itself of the cells, and we feed this data and we train this model on exact data and already prepared very well and normalized very well to remove the differentiate between these images. After that, the process will trained, and in each epoch we create 15 epoch And to prevent this evoke, we make augmentation to enhance the image every times, and to prevent that model from knowing the same image, and to force the model of learning.
Okay. Thank you very much.
Thank you.
Are there any other questions? No? Okay, so we thank the speaker.
Thank you.
Very much.
Thank
again.
you. Thank you very much.
Yeah.
Thank you.